Okay, we will continue from yesterday. We have done rational functions with horizontal asymptotes. And now we will see more cases where we have slant asymptote. So this is still 3.5. This is still 3.5 part B, the case where we have a slant asymptote. And if we can go further, we will talk about the ones that have curvilinear. Curvilinear asymptote. It helps us with the far-end behavior. Okay, but you will see that the concepts that we do in slant asymptote is very similar to the one in curvilinear case. Let's say, for example, I work on number 38. On number 38, we have let fx equals to 2x squared minus x minus 3 big over x minus 2. So let's factor this. This will be 2x minus 3 and then x plus 1. At the bottom, we have x minus 2. Now, from there, using the factored form, we can find the domain, which is all real numbers except 2. Part B, the y-intercept is 0,3 over 2 or 0,1.5. Part C, the x-intercepts are 2x minus 3, x plus 1 is equal to 0. So x equals to 3/2, x equals to -1 are the zeros because both of them real numbers. Then it translates into x-intercept 3/2, 0, which is also 1.5, 0. And -1, 0. Part D, vertical asymptote, that's x equals to 2. Part E, horizontal asymptote, there's none because the degree on the top, 2, is greater than the degree at the bottom, 1. However, we have slant asymptote because even though it's more, it's exactly 1 more. The degree on the top is exactly 1 more the degree at the bottom. So to find the slant asymptote, we will divide 2x squared minus x minus 3 divided by x minus 2, or actually, because the denominator is x minus c's form, I can use syntactic division. Okay, so the slant asymptote is given by y equals to 2x plus 3. That's the slant asymptote. Now I will just go ahead with the graph, okay? RG. So I skipped the sine graph. RG. I have. This is the graph. Okay, and then what else we know? The y-intercept is 0, 1.5. Use 0, 1.5. That's it here. And then the x-intercept 1.5, 0 and -1, 0. vertical asymptote x equals to 2. X equals to 2, let me put it here. This is x equals to 2. And then the slant asymptote will be y equals to 2x plus 3. 2x plus 3. So say it's like this. But the slope is 2. I don't like this. The slope should be 2. So approximately like this. Okay, let me extend it further here. So let me extend it further. Okay, so this is x equals to 2 here. This is y equals to 2x plus 3. Okay. Then we don't do sign graph. We don't do sign graphs. Therefore, the way I do the graphing here based a lot on intuition. Now, notice that I will say that the graph will, of course, will start from the slant asymptote, right? Okay, but we don't know is it from above or below. Okay, I will say it's from below, and then it goes this way, go down like this. Now, because the multiplicity of the critical number at x equals to 2 is odd, then it will change sign to positive infinity here, and then it will go this way. Okay. Now, to get more detailed about this, we can do the following. For example, one extra stuff, the slant asymptote intercept. So if the function, the graph of the function intersect with the slant asymptote, then I will set the function to be equal to the slant asymptote. That's the key. Okay. The function is 2x squared minus x minus 3 over x minus 2. The slant asymptote is 2x plus 3. Okay, now we don't know if there's any intersect though. Okay, I guessed earlier that there won't be any, but there could be somewhere. Okay, so 2x squared minus x minus 3 equals to x minus 2 times 2x plus 3. On the right hand side, I will get 2x squared minus x minus 6. So I end up with, we cancel the 2x squared, we also cancel the negative x, we get negative 3 equals to negative 6. That's incorrect, that's contradiction. Because of that, then no slant asymptote intercept. It doesn't intersect with the slant asymptote. That's how I know that in the earlier region here, there's no intersection. Okay, there's no intersection. Now, but if you want to go further into when will that be above or below x-axis, to see above or below x-axis, above, below x-axis, then you try to do the sine graph of the function, which is 2x minus 3, x plus 1, x minus 2. Okay. Sine graph of that function, I do it fast here. The critical numbers are negative 1, 1.5, and then 2. This is undefined here. Zeros are here. Will be plus, minus, plus, minus. You see that to the left of negative 1, it will be below x-axis, also between 1.5 and 2. to the left of -1, it's below x-axis, and between 1.5 and 2, that's also below x-axis. Okay, while between -1 to 1.5 above x-axis, above 2 also x-axis. Between -1 to 1.5, and also between 2 to infinity is above x-axis. Okay, but you may have issue with how do we know it is below or above the slant asymptote? If you want to find out if it is below or above slant asymptote, then we can do this analysis. Below or above or below, above or below slant asymptote. What you do is you do sine graph of the function minus the slant asymptote. Okay? So if this is positive, then the function is above slant asymptote. Okay? So this is 2x squared minus 3 minus x minus 3 over x minus 2. Is it right? Okay. Minus the slant asymptote, which is 2x plus 3. Okay, that's the slant asymptote. Now let me simplify this a little bit. This will be 2x squared minus x minus 3 minus 2x squared minus x minus 6 over x minus 2. As forward, I will get 3 over x minus 2. So according to the sine graph, we have only one critical number here, which is x equals to 2. Will be positive to the right of that, negative to the right of that. Now this means between 2 to infinity, that's above slant asymptote. And between negative infinity to 2, that will be below slant asymptote. Okay? So you see, between negative infinity to 2, it will be below slant asymptote, right? And between 2 to infinity, it will be above slant asymptote. Okay, that's the analysis. That's the analysis. Let's do one more question like this, the one with slant asymptote. Yeah, because I always have that kind of question in my test anyway. Later on in calculus, then you will learn where will we get the local minimum here and the local maximum here. Okay, where do we get the local minimum and local maximum? Okay, and therefore we can find the range of this function. But we actually, for this question, we can find the range of this function once we get to 4.1. But I will teach that to you later once we get to 4.1. Okay, let me do one more problem about this slant asymptote, and then we go on to the curvilinear asymptote. Number, what's good one? Number 40. I don't see anything else that is actually good. Yeah, number 40 is the one I can think of. Number 40, let me do it here. Fx equals to x cubed plus 1 over x squared minus 9. If we factor this, it will be on the top difference of cubes. Don't forget that plus 1 x squared minus x plus 1 over x plus 3 x minus 3. So part A, the domain is all real numbers except negative 3 and 3. Part B, the y-intercept will be 0, negative 1 over 9. Part C, the x-intercept, this one is a bit tedious. Its degree of 3. So we already have x plus 1, x squared minus x plus 1. So we already have negative 1 as an x-intercept, right, later on. Okay. But I need to show that the second part here, we need to look for another x-intercept here. It's degree of 3, right? It's degree of 3. So we're supposed to get 3 zeros. You will see these 3 zeros. One of them is real. The other one, the other two are actually complex. And the complex actually coming from here. You see the A equals to 1. The B is negative 1. The C is 1. So the discriminant is negative B minus 4AC. That's 1 minus 4, which is negative 3. So the zeros, even if any, maybe I say that here, so 2 complex, non-real complex zeros. Now, if you remember the conjugate zero theorem, okay, let me go on. So the zeros are negative b plus minus square root of the discriminant over 2a. Now notice that I can write this in square root of 3i for the complex, right? And notice that this x1 and x2 actually conjugate to each other. I hope that reminds us to conjugate zero theorem. In other words, if you have any non-real complex zeros, okay, or maybe irrational zeros, then those zeros has to be coming in pair. Okay, now because they are not not real numbers, so because x not real numbers, so no x-intercept from this branch. Okay, no x-intercept from here. We have only one x-intercept in this case. Now let me go on to the boundary partition. I try to save some space, that's why. How about the vertical asymptote? Part D, vertical asymptote. X equals to negative 3, x equals to 3. Horizontal asymptote is none because the degree on the top is greater than the degree at the bottom. Okay. That's why I set up the notation since yesterday, so that we don't have a lot to write. Otherwise, you need to assume because the degree of the numerator of fx is greater than the degree of the denominator of fx. Once you get the notation, that will be even faster. How about the slant asymptote? Yeah, notice that n is, which is the degree of 3, is 1 more than the degree at the bottom, which is the degree of 2. Okay, so I can actually divide it, and when I divide, I will get a linear equation. Give me a second. Huh? Now the top one is degree of 3 with a lot of placeholder, 0x squared plus 0x plus 1, yet the denominator x squared minus 9. X squared goes to x cubed, x times 1 time 1x, so it will be x cubed minus 9x. And when I subtract, I get 9x plus 1, whose degree is already less than the divisor. So we can stop there. So the slant asymptote is y equals to x only, whatever the quotient without the remainder. Okay, now we are ready to work this out. So let's say, oops. Let's say this is my coordinate system. Try to make it big. And then what are the x-intercept, y-intercept? Y-intercept 0, negative 1, 9. So slightly below the y at the x-axis. This is negative 1 over 9. And then how about the x-intercept negative 1, 0, x-intercept negative 1, 0. Vertical asymptote, x equals to 3, x equals to negative 3. It's x equals to 3, and x equals to 3, here approximately. X equals to 3. And then we have slant asymptote, y equals to x. So y equals to x approximately. It must cross the origin, right? It must cross. So it looks like that. Now, we know that we will come from the slant asymptote in this case, right? Now, the thing is, will that go up or will that go down? Now, the thing is, if it goes up, then we must have an x-intercept here, which is not the case according to our computation. Right? Okay, so no, it's not that one. It's not that one. It must be the one from below and go down. Okay, now, and then we know that x equals to negative 3 is a critical number with multiplicity of 1, so it must change to positive infinity, and later on it will go this way. And 3 is a critical number with odd multiplicity, so later on to the right of that it will look like this. So using the multiplicity of critical numbers tells me how they will behave. Okay, tells me how they will behave. Now, the thing is, can we find out the intersection here? Or if there's other intersection anywhere else? Actually, I don't know though. There could be other places. Okay, now to find that, the slant asymptote intercept, what I will do is I set the function to be equal to the slant asymptote and solve it. Okay, the function fx is x cubed plus 1 over x squared minus 9. The slant asymptote is x. So I get x cubed plus 1 equals to x cubed minus 9x. With that solved, I get negative 9x. So So x equals to -1/9. So the position here, the coordinate here must have x to be -1/9. Okay. And the y will be, how about the y? Well, we know that that line is y equals to x, right? So if the x is -1/9, the y will also be -1/9. So this guy will go here. Okay, now from here we also prove that there's no other slant asymptote intercept. Okay, there's no other slant asymptote intercept. And furthermore, actually, we can say even more that the range of this function is -infinity to +infinity. Now, look at the middle graph here, the middle portion of that graph. The middle portion of the graph is -infinity to infinity. So the range of the whole function will be from -infinity to infinity as well. Now, the last part, the curvilinear asymptote. Asymptote. Basically, the far end behavior of irrational functions where we have px on the top and qx at the bottom, with the degree on the top more than the degree at the bottom, follows the leading term of px over leading term of qx, which will be the leading term of the numerator over the leading term of the denominator. Well, because you will see that the numerator, the dominant one will be the leading term, and on the denominator, the dominant one will be the denominator. Right? Okay, so it will follow this curve. So when you go far enough to the right and far enough to the left, it will follow this function. I should say it will follow this power function. If you read in 3.1 what is power function, okay? For example, let fx equal to, I pick question from number 42. Number 42, let fx equals to x to the 5th minus 3x cubed minus x squared plus 1 over x squared minus 3. I think the top one I can factor. The top one, the first two terms I can factor x cubed, so I get x. Okay. No, it's not factorable. No, it's not factorable. It's not factorable. Can we factor it in any way? There's no way for us to factor it. Well, they just want us to find out the curvilinear asymptote. So I will not find the x-intercept. I will not find the y-intercept. Actually, y-intercept is doable, right? But the far end's behavior will follow the curvilinear asymptote will follow y equals to x cubed over x squared, which is x cubed. X to the fifth over x squared, that's y equals to x cubed. So you will see that when we sketch the graph later on, when we sketch the graph later on, the graph may be some kind of like behave within certain way, but when you go very far to the left or very far to the right, then you will see the graph actually get closer to x cubed. Okay, so the way the graph behave in the middle here, we don't know. But when you go far enough to the left or to the right, then it will get closer to this shape here. Okay, it will get closer to that x cubed. Now, let's see what the graph look like if we graph it. So y equals to x to the fifth minus 3x cubed cube or x cubed minus x squared plus 1 over x squared minus 3. So we have a vertical asymptote at x equals to radical 3 and x equals to negative radical 3. That's something we get from the denominator. Okay, let me zoom it out. Press enter. That's what the graph looks like. That's what the graph looks like. Let me zoom it further out. So you see something down there? Okay. Maybe I zoom it in there so that we can see that. So when we get far further to the right hand side, we go further to the right hand side, you see the curve on the right hand side. Okay. And let me zoom in. And when we go to the left, it will get like that. Now, let me superimpose, get a new equation here. Y equals to x cubed. Now, I hope by showing you this, then you understand what it means to be the curvilinear asymptote. Basically, in a very far end behavior, right? Eventually, the curve, the rational function, will get closer to that curvilinear asymptote. Do you see that? The red one and the purple one gets very, very close, right? The red one and the purple one get very, very close. Okay, but in between, they behave actually erratically, right? Okay, the function fx, the purple one, behave erratically in between, but when it goes very far to the right or very far to the left, then it gets closer and closer to x cubed. You see? The purple one gets closer to the red one. Okay, now that's what we meant by curvilinear asymptote. Okay, now then that helps us then to answer the following question. That helps us to answer the following question. So, for example, if somebody asks, as x goes to infinity, then fx will go to what? Then take a look on the curvilinear asymptote. the curvilinear asymptote x cubed now, and the behavior of this function will follow the behavior of the graph of x cubed when you go very far to the right and also when you go very far to the left. Okay, sorry, we get disconnected earlier. Let me make sure that we go back here. Yeah, we get disconnected earlier. I don't even know when did we get disconnected. Well, anyway, the suggested homework from 3.5b, the second part, will be from 37 to number maybe to number 53. To number 53. Okay, to number 53. That's for this 3.5b. Let me write it down there. Now the next section is the easy one, 3.6. It's very easy to the point that, as I remember, I hardly ask any question from here. But you still need to know the terminologies that we will use a lot in calculus for this 3.6, which is variations. You have learned this in intermediate algebra, though. And at this point, there's almost no difference between what you learned there and what you learn here, variation. There are two terms that you need to know, terminology. Okay, now y varies directly as x. Or simply y varies as x. The common terminology being used is varies directly, okay? But the other two, y varies as x, that actually have the same meaning, or y is directly proportional to x, or simply y is proportional to x. Now, these four phrases here means the following. It means y is equal to a constant multiple of x. Okay, as if you are saying that if we double the x, then the y is double too. Okay, if you triple one of them, then the other one also triple. That's what we mean by direct variation. Okay, that's what we meant by direct variation. Okay, let's do one example. Let's do one example, simple one first. Maybe I do the other one right away then. It's way too simple that I just do both at the same time. Okay, that's for direct variation. And the other one is inverse variation. Inverse variation. The terms they use will be y varies inversely. Y varies inversely as x. Or y is inversely proportional to x. Only two phrases to pass. They have to use the word inversely when it is inverse variation. They don't need to use the word directly if it is direct variation. Okay, but if we have inverse variation, it means y equals to k over x, which means if we double x, then the y is half. Okay, the other way around. Okay, now I think that's actually the best way to actually memorize these terms, but you can also think this way. When we say directly proportional, it means the proportion is always constant. That's directly proportional. If one of them increase, then the other one has to increase also to keep the ratio, to keep the proportion. While inverse variation means the product should be constant. So if you double one of them, the other one needs to get half such that the product is the same constant. Okay, now that's what direct variation and inverse variation means. This case here, in both cases, direct or inverse variation, this K is called constant of variation. Or constant of proportionality. Now we call that constant for proportionality, especially if we write it this way. Okay, but I know in some textbook, instead of calling them constant, some textbook also call them coefficient of variations or coefficient of proportionality. Okay, that's those are the wording. Now let's do some problem. Let's do some problem. I will pick question from our book. The easy one first. From 3.6, section 3.6. Let's see number. Let's do number 6 right away. Okay. It says that W varies directly as C and inversely as square root of U. So what does it mean when we say W is a joint variation directly as C and inversely as square root of U? It means we can say W is directly as C, so that's KC, right? Inversely as square root of U over square root of U. Bang, that's it. Okay, now then, find K, first part, find K when C equals to 2, U equals to 9, W equals to 6. And plug in numbers for K. So W is 6 equals to K times C over square root of 9. That's 6 equals to 2K over 3. Okay, so 18 equals to 2K, K equals to 9. So what is the formula? Find the equation. The equation now becomes W equals to 9C over square root of U. That's the equation relating W, C, and square root of U. So later on, using this formula, when they tell you, oh, okay, you know what? If C equals to 10 and U equals to 25, what will W be? And then you can go on from here. Let me just write it down. Part C, find W when Z equals to, let's say, 8 and U equals to 25. And using the formula we have above, we get 9 times 8 over square root of 25. That's 72 over 5. So W equals to 14.4. Okay. Now our textbook only asks for coefficient of variation or constant of proportionality. Okay. Now let's do a harder problem. Number 16. Number 16, Y is directly proportional to the square of X and inversely proportional to the square root of C. Let's say the question is, find the formula or the equation if X equals to 5, C equals to 16, gives Y equals to 10. For that, we need to find the K first. Okay. So from the passage there, Y is directly proportional to K to X squared and inversely proportional to square root of C. Now then you plug in numbers. 10 equals to k times 5 squared over square root of z. So 10 equals to 25k over 4. So 40 equals to 25k. 40 over 25 equals to k. I think when you divide, you get 1.6. Huh? Is it right? Times 4 times 3, it will be 1.6. So the equation will be y equals to 1.6x squared over square root of x. Now that's for number 16. Now, and the rest of this section is actually word problems. The rest of this question here is word problems. Let me do one, and then after that, we give ourselves some break. Let me do, for example, number 24. Number 24. It is known from physics that the range of a projectile, is directly proportional to the square of its velocity. So from there we see that r equals to k v squared. From that one sentence only. Okay, and I happen to answer part A. Part A, express r as a function of phi by means of the formula that involves a constant of proportionality k. Now then part B. Part B, a motorcycle daredevil made a jump of 150 feet. So that's the range, 150 feet. If the speed of coming off the ramp is 70 miles per hour, so phi equals to 70 miles per hour, find the value of k in part A. So 150 feet equals to constant of proportionality times 70 squared. So 150 equals to 4,900 k. Okay, so k equals to 150 over 4,900. I think I can cancel one of the 0, and I still can reduce by 5, I believe. Let me reduce by 5. If I reduce by 5, I get 3. Reduce by 5, I get 98 here. So that's the constant of proportionality. Now then, using that result, then the question is, find the range when the initial velocity when it came off the ramp is 80 miles per hour. And that will be r equals to 3 over 98 p squared. That's the formula. Now I plug in the numbers to find the r. R equals to 3 over 98 times 80 squared. And you can use your calculator for this. 3 times 80 squared divided by 98, I get 195.92 feet. Okay, that's for this section. Your suggested homework, you don't need to do a lot here. Just do every other odd from number 1 to number 27 to every other arc. I think they're too easy. That's why I don't need you to do too much problem from there. Okay, right now it's 12:06. Let's take a break. We come back at 12:16. Okay, let's start again. We will then go on to 4.1. It is on inverse function. 4.1 inverse function. This section is also another long section. This section is also another long section. Now, we will first talk about something called a one-to-one function. Let's recall that definition. A function is a correspondence or relation from one set, which we call domain, to another set which we call range, such that each element in domain corresponds to or relates to exactly one element in the range. From the mapping, suppose we have the domain here and the range here. Then any element you have in the domain will correspond to exactly one element in the range. So basically, from each element in the domain, there will be one arrow coming out from each element here. That's for a function. So once you have any branching from any element in the domain, then it is not a function anymore. Okay, so from each element in the domain, you have only one arrow coming out corresponds to one element in the range. Now, this is for a function. And what is a one-to-one function? Definition. A function is one-to-one if beside each element in the domain correspond to exactly one element in the range, the converse also true. If each element in the range corresponds to one element. Give me a second, something important. One element in the domain. Okay, so basically what we have is then not only each element here correspond to one element there, but each element in the range corresponds from only one element in the domain. Okay, that's a one-to-one function. So for each element in the domain, we have it corresponds to one element in the range, and for each element in the range correspond to one element in the domain. That's what we call one-to-one. Now, one-to-one can also be understood as that from one element in the domain goes to exactly only one element in the range, and that one element in the range comes from actually one element in the domain. So the mapping that we see above here is not one-to-one. It is a function, but it is not one-to-one. Okay, it is a function, but it is not one-to-one. Okay. Now, one of the consequence of this definition, consequence, is this, something called horizontal line test. Horizontal line test. That says that function fx, function fx is one-to-one if the graph satisfies horizontal line test. What is horizontal line test? That is every horizontal line will intersect the graph. I think I would say every horizontal line intersects the graph. Intersects the graph at most once. For example, the graph of every linear function whose slope is not zero, y equals to, let's say, 2x minus 1, whose slope is not zero, so this is the coordinate system, and the graph is this. Graph is this. Let's say something like this. Okay, now notice that every time you draw a horizontal line, it will hit the graph at most once. It will hit the graph at most once. Okay, it will hit the graph at most once. Now, if that graph has that property that in whatever horizontal line you draw, it will hit the graph at most once, then that graph is one-to-one. Okay, then that graph is one-to-one. Now, Then from there, we will see that the graph of y equals to x squared or y equals to absolute of x, those are functions, but those are not one-to-one. The graph of x squared, as we know, looks like this, right? The graph of absolute of x looks like this. Let's do the sketch. Looks like this, right? So you see that we can easily find a horizontal line that intersect the graph at more than one place. Okay, so these two functions are not one-to-one. They are functions, but not one-to-one. Okay, so this is one-to-one. And these are not one-to-one. Now you will see the following, that you will see a little note, but it's quite important. A function, a continuous function, that is strictly increasing, like that 2x minus 1, or strictly decreasing, must be one-to-one. Okay, if it is increasing, strictly increasing, or strictly decreasing, then it must be one-to-one. Okay. Now let's go on to inverse function. Definition. Let fx be a one-to-one function with domain D and range R. And range R. Then a function, another function, gx with domain R and range D, is the inverse function of fx if fx equals to y if only if gy equals to x. Now, this definition may be a bit confusing, but I prefer to say it in two different ways. To rephrase it in two different ways. In other words, G G as a function cancels what f does. I usually say G undoes from the word undo. G undoes what f does, and f undoes what G does. Now, pictorially, let's say this is the domain D and this is R, the range R for the f, right? So if you have x here, f will send that x to y, and G will send that y back to x. Okay? Such that basically the more precise definition of inverse function gx is the following: f compose g of x equals to x for x in R, because R is the domain of G, and G of f of x is equals to x for any x in D, which is the domain of f. That's the definition of inverse function. And we denote, in this case, then, note, if G is the inverse of a function of inverse function of f, and G is also denoted by f inverse. Now, to be more precise, if I use gx here and fx here, then gx is f inverse of x. Okay. Now, this notation is not the same. F inverse x is not the same to 1 over fx. No, they are not the same. Okay, that notation 1 over fx is written as fx to the power of -1. Fx to the power of -1. Okay, so it's the whole function that taken to the power of -1. But if only f to the power of -1, that's the notation for inverse function. Okay, now some exercise. I honestly get disturbed a little bit with my my pen, the pen that I used to write here. It keeps on calling for another function that I don't call. For example, let x equals to 2x minus 1. Now we know that f3, for example, is equal to 5. Okay, so the inverse function will send 5 back to 3. So you can imagine if 3 here, and the function will send the 3 to 5. That's what the function is doing. Okay, now then inverse function of 5 will send it back to 3. Okay, now don't forget that the inverse of a function is a function only if it is one-to-one. Only if it is one-to-one. Okay, so suppose I ask you this question: what is f inverse of 10? Now that's the same to us. F what equals to 10. Okay, f what equals to 10. You need to solve for x such that f of that x gives you 10. Okay, but this is also means that you can solve it this way. Then 2x minus 1 equals to 10. 2x equals to 11. X equals to 11. 2, which is 5.5. Okay, so f inverse 10 is 5.5. Or another way to say it, f of 5.5 equals to 10. That's for inverse function. Again, I get really annoyed by my hand right now. I guess I need to fix it first. And for me to fix it, I need to take a little break here. Let me take a little break to fix my. Well, you know what? Let me just write it down for now. So let me go on. Procedure to find inverse function. F inverse x given, if you give me a one-to-one function fx. So the starting point has to be a one-to-one function fx. So step 1 will be, and in your test, I need you to write it this way: 1, 2, 3, 4. There will be 4 steps. Step 1 is replace fx by y. That's the first step. Okay, so suppose, for example, I have that fx equals to 2x minus 1, right? So to find the inverse function, I replace the fx by y first. Step 2, swap x and y. So in step 2, x becomes y, y becomes x. You will see it's actually in the second step the inversing happens. Inversing happens here. Step 3, then we solve for y. So in step 3 here, I add 1 both sides and then divide by 2 to solve for y. And then in step 4, replace y by f inverse x. F inverse x equals to x plus 1 over 2. Okay. Now, I would like you to try some examples while I fix my pen. For example, I would like you to find inverse function of the following one-to-one function. First one, suppose I have fx equals to, let's say, 3x plus 4 over 2. And then the second one, fx equals to x plus 2 cubed minus 4. Try these two questions first, and then maybe I give 5 minutes, and then later on I will go over that and do more problems to find inverse function. But the procedure will be like that. Okay. So basically, you need to get used to deal with applying these 4 steps. Okay. First one, you have fx equals to 3x plus 4 over 2, and then we need to find inverse function again. So my step 1, I replace the fx by y. Step 2, I swap the x and y. Step 3, I solve for y. This is the one that usually takes longer step. And then solve for y. And multiply by 2, and then subtract by 4, divided by 3. And step 4, let me do it here. F inverse x is equal to 2x minus 4 over 3. Now later on we will take a look on the significance, the comparison between the graph of fx and inverse of f. That's for part A. Part B, step 1, I changed that to y. And then step 2, I swap the x and y. Step 3, I solve for y. So I add 4 both sides first. And then to undo the cube, I do cube root. And then subtract by 2. Last step, f inverse x equals to the cube root of x plus 4 minus 2. Okay, now those are for those two questions in our early examples. Now, the next thing are two or three common questions I asked in my test, but it's more into the conceptual and algebraic foundation. The first one is the following. For example, let fx, let me use gx this time. Let gx equals to x minus 2 over 3x plus 4. You will see that this function is actually one-to-one. We have learned to graph this back in chapter 3, 3.5. When we graph this, the vertical asymptote is negative 4 over 3. It's negative 4 over 3. Let me put it here. And the horizontal asymptote is y equals to 1/3. The y-intercept is 0, negative 1/2, approximately here. And the x-intercept is x equals 2, 0. This is negative 1/2 here, this is 2 here. And the graph will be approximately like this. And you can tell from this graph that it satisfies horizontal line test. It satisfies horizontal line test. Every horizontal line graph will hit the graph of gx at most at one point. Okay, so yes, we have learned from the past that this is a one-to-one function. Now, of course, if I ask you to find the inverse function, you have to assume that it is a one-to-one function. Okay, that's how we can get the inverse function. That's how we can get the inverse function. Now, then, what is the domain here? The domain of this function is all real numbers except negative 4/3, right? From the graph, you see, from the graph, for now, from the graph, we see that the range is all real numbers except 1/3. Right? Okay. Now, we will use inverse function to systematically and not relying on intuition, not relying on the graph, to find the range. Okay. What we will do first is to find inverse function. So find inverse function g inverse x. Step 1, y equals to x minus 2 over 3x plus 4. Step 2, I swap the x and the y. So don't forget that procedure though. Only by practicing enough you will remember that procedure. And then step 3, I will solve for y. Multiply by the LCD. Isolate the y. Factor the y. And divide by 3x minus 1, negative 4x minus 2 over 3x minus 1. So the inverse function G inverse x, the inverse of gx, right? So is negative 4x minus 2 over 3x minus 1. We can actually, by the way, we are done with the inverse function. Okay, but you can actually factor the negative 2 out. And I will reverse the order of subtraction at the bottom to get rid of the negative on the top. Yeah, because when you reverse the order of subtraction, you get the opposite. Okay, so either you use this as your inverse function or you use this as your inverse function. Either one will give you exactly the same thing. Okay, now, but one thing we learned from before, the analysis about the domain, the range. The range of the function, as we have seen earlier in the definition of inverse function, the range of the function is the domain of the inverse function. So if you want to know the range of the gx, the one that we did by intuition earlier, that's all real number except 1/3, okay? We actually look at the inverse function and see what's the domain here. The domain of G inverse x is all the x where x not equals to 1/3. Right? That's the domain of inverse function of x. So that gives us the range. The range of gx, therefore, is all the y where y cannot be 1/3. Now, that's the same to what we have said earlier, all real number except 1/3. But the way we said that earlier relies heavily on the graph and intuition. But right now, we actually solve that range problem using a more systematic and less intuitive method. Okay, it's more from the algebra. Okay, so what I want to say is in pre-calculus, there are three things that you need to be able to connect. First, the algebra. Second, your intuition. Third, your graph. Those three should be in line. Now, why? Because there will be times, as you will see later on, we are not able to graph it, so we will rely on the algebra. Okay, like the one here, like the one here, like the one here. Part B here. Okay. Can we find the inverse function without graphing it? Right? And then how about the domain question? What is the domain of this guy? Well, this is polynomial, right? Because if you expand this, you will get polynomial minus 4, that will still polynomial. So the domain will be all real numbers. But how about the range? How about the range? Now, to find the range of that function, then we look at the domain of the inverse. The domain of the inverse, that's cube root. That's cube root. So there's no restriction on the radicand. X plus 4 can be positive, can be negative. So the domain of inverse function, the domain of f inverse x is all real numbers, which means, therefore, the range of the original function will be also all real numbers, which we actually confirm. This is degree of 3, right? So when we expand this, this will be a polynomial with degree of 3. The far end behavior will be bottom top. So when you go very far to the left, it will be, the value will be negative infinity. If you go very far to the right, it will be positive infinity. So the range, as we have learned before, is all real numbers. Okay, but after break, we will do some situation that is not clear. First, to tackle some problems in the book. What happens if we don't have a one-to-one function, but how to make it one-to-one? And second, what happens if the function is not one-to-one to start with? Okay, but let's take a break. Right now it's 1:06. We take a break, come back at 1:16. Let's continue. Still continue on this inverse function. Let's take a look on the graph. Let's take a look on the graph. But when we do the graph here, I prefer to let's go back to this one first. Let's go back to this one. Review first example. One of our example earlier, that fx equals to 2x minus 1, then f inverse x is x plus 1 over 2, which is 1/2 x plus 1/2. Happens to be something we can simplify easily. Now, let's take a look what the graph look like. Okay, let's take a look. I use simple graph because these two are actually graph that we still can do easily. Okay, you see that 2x minus 1, the graph of 2y equals to 2x minus 1 is aligned with slope 2, okay, y-intercept 0, -1. So you can say approximately like this, Okay, this is y equals to 2x minus 1, while the graph of 1/2 x plus 1/2 has the slope 1/2 and the y-intercept 0, 1/2. So it looks like approximately like this. Approximately like this. It's y equals to 1/2 x plus 1/2. Now we will go much more in the detail right now as the following. Notice that the x-intercept, the y-intercept first of the original function, the y-intercept is 0, -1. Okay, now that y-intercept for the original function relates to the x-intercept of the inverse function. Yeah, you can try to find the x-intercept of this fx here. Try to find the x-intercept of this fx, this function here. And you will get x equals to -1, such that the x-intercept is -1, 0. Likewise, the x-intercept of the original function fx is 1/2, 0, which is the y-intercept in the inverse function 0, 1/2. Now, remember I told you that the inversing happened when you swap the x and y? That's actually because when we swap x and y, we basically reflect the graph with respect to this line. We reflect the graph with respect to this line, y equals to x. Okay, so x becomes y, y becomes x. So that's what happened. You swap that around, that y equals to x line. Okay, and therefore, because of that swapping, then the domain of the function, the domain of fx, is the range of f inverse x, and the range of the function, the domain in fx is equal to the range, of f inverse x The range of the original function can be obtained by finding the domain of the inverse function. Okay. The y-intercept of the original function correspond to the x-intercept of the inverse function. I should say correspond here, not exactly equal. And x-intercept of the function corresponds to the y-intercept of the inverse function. Okay, in calculus 2, you will go even further. One of them is looking at the slope of the line if you have a line. Now I use an easy function here. I use an easy function. I really don't know what happened with my pen. Something like that. See, oh, that's not what I want. Oh, I'm sorry, I get distracted. But it's not only for this function though. It's also for other type of function. Let's say, for example, let's take a look on our graphing paper, graphing software. Okay, suppose we have y equals to x cubed minus 4. X cubed minus 4, let me zoom it out a little bit. Okay, now that's what x cubed minus 4 look like. Now you try to find the inverse function. Okay, try to find the inverse function. But once you find the inverse function, you will see that the graph looks like this. Y equals to the cube root of that will be the cube root of x plus 4. Okay, the cube root of x plus 4, something not right here because it's supposed to have, that's the limitation of this graph though, but it's supposed to have the tail here. Okay, my computer deal with the, will deal with this radical only when the radicand is positive. But you see that whatever the graph that we see between the green, between the purple and the red one, okay, if I go on with a new graph, notice that that's basically the reflection with respect to this line here. Okay, so the purple color, when you reflect that, you will get the red one. Okay, even though, yes, something missing from the red one there. We have these tails missing. Okay, so doing inversing will swap the role of x becomes y, the role of y becomes x. We will use this property later on when we get to a logarithmic function. Okay, you will see tomorrow when we go for 4.2 and 4.4, logarithmic function is exponential function is 1-to-1. Therefore, the logarithmic function also 1-to-1, and the graph is actually with its reflection with respect to x equals to y equals to x line. Let me go back to our notes. Okay, now remember these notes here. Remember these notes here. Okay, very important. You can solve a lot of problems that even tutors find to be difficult and turns out to be doable using this point of view here. Now, from here, I have a couple of things to say. First one is this. What happens if you have a function that is not one-to-one? How to make it one-to-one? Okay. If a function is not one-to-one, then one way to make it one-to-one, one method to make it one-to-one is by restricting the domain. The domain. Okay, now let's say for example, number 34. So we are still dealing with the material from our textbook. The notion of the concept of inverse function is actually something we have learned even in intermediate algebra. So the procedure that we have done here is actually nothing really new, except that I emphasize more in the domain and the range and reflection with respect to that y equals to x line. Okay, now starting from this number 34 here is something you especially see in precalculus, you didn't really see in intermediate algebra. Suppose number 34, we have fx equals to 5x squared plus 2, where you restrict that to only x greater or equals to 0. Okay, so remember, quadratic function is not supposed to be one-to-one, right? Quadratic function is not supposed to be one-to-one. Okay, but then if you restrict the domain to x non-negative, so if I sketch this, it looks like this, right? Okay, it's not one-to-one until I restrict that only for x greater equals to 0, then we get only this part. Now notice that if you only take a look on the blue part there and you do horizontal line, it will hit the graph at most once. Okay, so then one way to make it one-to-one is by doing such restriction. Now then, going back. Second, I want to turn off that. Then how to find the inverse function? Once it is one-to-one, then it is a common question to ask, what's the inverse function? So step 1, y equals to 5x squared plus 2. Now, if I were you, I will still write this thing, the requirement, x is greater equals to 0. Now then, when I swap the x becomes y becomes x, then this also swap, right? See what I think? Now then step 3, I solve for y, x, and what happened? I got really frustrated with my pen today. So x minus 2 equals to 5y squared divided by 5x minus 2 over 5 equals to y squared. But don't forget the y has to be non-negative, right? Now, why I need to keep track of that y? Because of the following. When I apply the square root, I'm supposed to have plus minus. Now, together with the fact that y is non-negative, then we get that y has to be the positive branch, not the negative branch. Okay, therefore, then I get y is the step for f inverse x is the positive branch instead of the negative branch of x minus 2 over 5. Number 38, that's another case. Number 38, fx equals to the square root of x plus 4. Okay, now notice that fx is positive here, not negative. Okay. They don't tell us this, but implicitly from that function, we need to get the positive branch. Right? Okay, now then let's see what will happen later on. Okay, why we need that? Step 1. Step 1, y equals to square root of x plus 4. Step 2, x equals to square root of y plus 4. But this is y greater equals to 0. Therefore, this is x greater equals to 0. Now, notice that here's the thing. When we square both sides, we may have extraneous solution, right? We learned that from, I think, chapter 1. When you square both sides of an equation, then you may have extraneous solution. Now, notice that without this restriction here, then my x may be positive, may be negative. Do you notice that? Right? Okay. And therefore, my sorry, I'm not done with step 3 yet. So x squared minus 4 equals to y. Then step 4, f inverse x is x squared minus 4. But something wrong here if you don't use that restriction. If you forget to write this x is greater equals to 0 in this case, notice that the graph of this x squared minus 4 is not 1-to-1. But that's impossible. That's impossible. Okay? If fx is 1-to-1, which we know it is, right? Fx is 1-to-1 from here, right? The graph of this thing here, looks like this. It looks like this. That's 1-to-1. So the inverse of that should look like approximately like this. Now notice that that's the reflection with respect to y equals to x line, right? Okay. Now, but if I don't have this restriction, then the graph of that x squared minus 4 will be like this, which is not 1-to-1. So that's a violation, something not right there. Okay. It has to be 1-to-1 for us to find the inverse. And the resulting inverse function has to be 1-to-1 also. Okay, that's why it's the fact that we need to have this restriction becomes something very important. Okay, don't forget that restriction. If fx is 1-to-1, then the inverse function needs to be 1-to-1 as well. Okay, keep this in mind. Extremely, extremely important. Okay, in fact, I penalize here and there on test 2 because of that lack of detail. Okay, you're in pre-calculus, you need to see that detail. Okay, you need to see that detail. Pre-calculus is not a place where we fix what you miss from intermediate algebra. No. Yeah, we do some review, but we need to actually cover more. If you just review what you have from intermediate algebra, just doing the same thing, the same difficulty level, then you will never get to pre-calculus. If pre-calculus is to review, then trust me, your calculus class will be the review of your pre-calculus. You never move on, okay? Yeah, so yeah, we need to move on, and that's when we need to know further, okay? Give me a second. Now, the next statement, the next thing I will do in the next 20 minutes or so is something not in our textbook. The following is not in our textbook. And I will make some statement that could be controversial for other instructors. But that's because other instructors didn't want to go tough. Okay, but I'm teaching you to pass calculus 1 and calculus 2. That's why I want to go this detail. Here's the thing. If a function fx is 1-to-1, then the inverse is also a function. Even further, it is a function and 1-to-1. And because of that, the inverse function has the right of bearing the functional notation. The inverse, because it is also a function, right? Can use functional notation, f inverse x. Okay, now nothing controversial with that. That's something we learned earlier. But I actually pay more attention to details that if a function is 1-to-1, then the inverse is also a function. That's why we call that inverse function. Okay, but the following is not really well accepted by those who don't think hard enough. What if the function is not 1-to-1? Now, some people say, if the function is not 1-to-1, then there is no inverse function. That is true. If the function is not 1-to-1, then there is no inverse function. Okay? Now, the keyword is the following. The keyword is the following. Actually, every function regardless is 1-to-1 or not, has an inverse. Every function has an inverse. If the function is 1-to-1, then the inverse is also a function. That's why we call that inverse function. Okay, now, so what happens if the function is not 1-to-1? Then the inverse still exists though. Okay, the inverse still exists. In fact, to find the inverse of a function, all you need to do is actually reverse the x and the y. Then you will get the inverse. Okay, now, but the inverse may not be a function. Okay, now because it is not the function, because of that, the inverse, because it is not a function, cannot use function notation. It has no such right. Because it's not a function, you cannot use function notation. Okay, you cannot. So why do you tell us this, Thomas? Well, I'm telling this because even though a function is not one-to-one, we still can find the range of that function. That's one technique that possibly used, not always, but possibly used to find the range of that function. Okay? To find the range of that function, one thing we can do is to find the inverse of that function. But because the function is not one-to-one, then the inverse is not a function. But we still can find the range of that function. We can find the range of the function by looking at the domain of the inverse. Notice that I didn't use inverse function notation here. Okay, now let's do one simple example here. Let's do one simple example. For example, let fx equals to x squared minus 2. Now we know the graph of this looks like a parabola with vertex 0, 0, shift down 2 units. Right? Okay. Now suppose I ask this question: find the range. We know we could answer this question even in our test 1. Find the range. We know the range is from -2 to infinity, right? Well, you can see from the graph. Okay, but can we do this more from analytic point of view? Yes, by finding the inverse. Okay, that's something we know before, right? But let's confirm that analytically. So step 1, I change the fx by y. Step 2, I swap the x and the y. Step 3, I solve for y. And I do plus minus square root of x plus 2 equals to y. Now notice that that's not a function because each x, there are some x's that give you 2 different y's. Okay, so I cannot go on with step 4. Okay, I cannot go on with step 4 because f inverse x is not a function. Okay, it's not a function. But we still can find the domain of this inverse though. The domain of the inverse of fx is all that x plus 2 has to be non-negative, right? Okay, therefore, x is greater or equals to -2. Does that make sense? Okay, now notice that this will also be the range of the function. Okay. Now, the reason I taught you that these 4 steps is because that we can use the same procedure to find the range of a function by looking at the inverse. And the inverse doesn't have to be a function. You don't need to finish this to step 4 to find the domain of that inverse function. No. Even if it is the inverse is not a function, you still can find the domain of that inverse, which implies the range of the original function. Okay? Now, I will do one problem that was actually from our 3.5 earlier. I would like to do, what's that? This question here. This question here. Number 38. Number 38. Let me lasso that. I just need this. Copy. Go to 4.1. Okay. Put it here. So this is from, again, this is from 3.5, section 3.5. I borrow this example. Okay, and then we are interested in find the range. Find the range of this function. Now notice that this question could not be done in 3.5. In fact, our textbook, even in 4.1, did not mention this at all. At all. Our textbook never mentioned this. But I want you to realize that pre-calculus actually go this far that we can actually find the range of this function. Not all though, not all functions can use this technique to find the range. No, not all. But most of the problems that we do in this course actually doable using this technique. Okay? Yeah. Now then, how to find the range? So what I will do is I find the inverse. So step 1, y equals to 2x squared minus x minus 3 over x minus 2. Step 2, I swap the x and y. X becomes y, y becomes x. Step 3, we solve for y. Now that's where we get stuck a little bit later on. We need to solve for y, right? We need to solve for y. The thing is we have y and x there. How do we do that, Thomas? Well, if you think about it, if you take a look at your x and consider that x as constant, then this is actually a quadratic equation. Let me rewrite it even further this way. This is 2y squared minus x plus 1y plus 2x minus 3. Where my a is 2, my b is negative of x plus 1, and my c is the one without y's. Okay, so you see this is the y squared term, the coefficient is 2. This is the y term, the coefficient is negative x plus 1. And the constant term is 2x minus 3. Now, remember that to solve this quadratic equation, first thing I usually tell you to do is to look for the discriminant, and the discriminant has to be positive, right? Okay, now, so the discriminant is negative of x plus 1 squared minus 2ac. This will be x squared plus 2x plus 1. You see the negative being squared just cancel. So I basically squaring x plus 1 minus, I'm sorry, this is 2x minus 3. This is 8x plus 12. So my discriminant is now becomes x squared minus 6x minus 11. Okay, now remember I told you that so the inverse, maybe I stop a little bit and then go on with the inverse. The inverse y will be negative b plus minus square root of d over 2a, which is 4. Okay, that's the inverse, which is not a function. Which is not a function. Maybe I write it in red underneath so that you know that you cannot do this, you cannot write this, because you see for some x's you have two branches. There are two possible values for y's. Okay, so we cannot write it as an inverse function, but we get the inverse nonetheless. Now then, what's the domain of that inverse? Domain of this inverse is when this guy inside the house is non-negative. Remember I said that the discriminant has to be non-negative, right? Okay, the domain of this inverse is x squared minus 6x minus 11 greater equals to 0. Okay, now then how do we solve this? Then we go to the solving nonlinear inequality method. Step 1, critical numbers. X squared minus 6x minus 11 equals 0. Let me do completing the square. Plus 9 both sides. If you ask me why we plus 9, negative 6 divided by 2 is negative 3. Whatever the quotient, we square it, we get that 9. That's how we get, we add 9. Okay, so we get x minus 3 squared is equals to 20. So x minus 3 equals to plus minus square root of 20, which is plus by 3 plus 2 square root of 5. Those are the critical numbers. Step 2, sum graph. Critical numbers, 3 minus square root of 2 square root of 5. And 3 plus 2 square root of 5, both of them the zeros. And then the sign graph will give us this plus, minus, plus. So the solution for this inequality, is, the solution for that inequality is this section here. Okay, the solution for that inequality is from negative infinity to 3 minus 2 radical 5 inclusive union 3 plus 2 radical 5 to infinity. Now, that's the domain of the inverse, right? At the domain of that inverse, we need to solve that inequality. But the domain of that inverse also the range. So the range of fx is negative infinity to 3 minus 2 square root of 5. Oh, with bracket, no. This is union 3 plus 2 square root of 5 to infinity. Okay, now you don't see this kind of question in the book, so you need to actually try to find out this kind of question in my old test. Okay, suggested homework from here. Suggested homework from here. From 4.1, number 1 to number 47. Number 1 to number 47. Okay, now there's some part there between number 5 to number 15. The question is, how do we know, determine whether is the function 1-to-1? Okay, there are two ways to do it. Okay, to show, and they are actually quite opposite. To show it is 1-to-1, what you can do is find the inverse. You try to find the inverse function. Try to find the inverse function. If you see that the inverse is a function, then it is 1-to-1. Okay, now, but how to show it is not? And to show that it is not 1-to-1, then you will find two values of x, two different values of x that give same y. So you still don't need to graph it though. So let's say, for example, is fx equals to x squared minus 4, 1-to-1. We know it's not, right? But how do we explain in writing without going too much into graphing? Because there could be a case that we don't even know how to graph it, right? Okay, what you can do is then find two different x's that give you the same y. Okay, so the solution, we will say no. Why? Because, just give a counter example. F2 equals to, maybe F3 instead of F2. F3 equals to 3 squared minus 4, blah, 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 that's 5. And F negative 3 will also give you 5. So you see that 3 goes to 5, but negative 3 also goes to 5. It is a function, but it is not 1-to-1. You see what I mean? Okay, so to show that it is not 1-to-1, all you need to do is to find two different values of x that give you the same value of y. Now, but how do we show that the function is 1-to-1? One technique, in fact, this technique may not be acceptable to other teachers, but most teachers will be okay with this, is to actually find the inverse function. This is where I will start for today. Tomorrow we go on with 4.2, 4.3, and 4.4. You can start studying from my old test tool already. Your test tool will be, don't forget your test tool. Test tool will be on July 17th. This Friday. Okay? And don't forget that this Friday, July 17th, when we say you have a test, you need to go on Zoom. You need to turn on your camera. You need to turn on your audio. Okay? I need to be able to see your head, your hands, and your desk. Anything else that you don't want me to see, you don't expect me to see because of your privacy, for example, then you need to evacuate them. Okay? That's actually, the burden is on yours to protect your own privacy. That's where I will stop. Oh yeah, the material for your test 2 will be from 2.7, as I remember. Let me say that again. Yeah, from 2.7, chapter 5, chapter 3, 3.1 to 3.6, and then 4.1 to 4.4. Yeah, we'll finish the material tomorrow. 4.2, 4.3, and then 4.4. Okay, but if you want to study from my old test, you can study from all those questions except exponential functions and logarithmic functions. So take a look in my old test too, and start working on those problems that doesn't have exponential function nor logarithmic function. And if you want to go ahead, starting from my old lecture, you can go to YouTube and see from summer pre-calculus class. Okay, that's for today. See you then tomorrow.